chemist Antoine Lavoisier. Like most scientists of the time, Lavoisier was a rich aristocrat who funded his own research. He and his wife, Madame Lavoisier, who assisted with his experiments, even commissioned the celebrated painter David to paint their portrait. Lavoisier carried out experiments to support the erroneous idea that heat was a substance, a weightless fluid that he called caloric.
He thought in the solid state of matter, molecules were just packed close in together. And when you added more and more caloric to this, the caloric would insinuate itself between these particles of matter and loosen them up. So the basic notion was that caloric was this fluid that was, as he put it, self-repulsive. It just tended to break things apart from each other. And that's his basic notion of heat. So cold is just the absence of caloric or the relative lack of caloric.
Lavoisier even had an apparatus to measure caloric, which he called a calorimeter. He packed the outer compartment with ice. Inside, he conducted experiments that generated heat, sometimes from chemical reactions, sometimes from animals, to determine how much caloric was released. He collected the water from the melting ice and weighed it to calculate the amount of caloric generated from each source.
I think the most striking thing about Lavoisier is that he sees caloric as a substance which is exactly comparable with ordinary matter, to the point that he includes caloric in his list of the elements.
Indeed, for Lavoisier, it's an element like oxygen or nitrogen. Oxygen gas is made of oxygen plus caloric. And if you take the caloric away, presumably the oxygen might liquefy. So it's a very hard model to shift because it explains so much, and indeed Lavoisier's chemistry was so otherwise extraordinarily successful. However, Lavoisier's story about caloric was soon undermined.
But there was one man who was convinced Lavoisier was wrong and was determined to destroy the caloric theory. His name was Count Rumford. Count Rumford had a colorful past. He was born in America, spied for the British during the Revolution, and after being forced into exile, became an influential government minister in Bavaria. Among his varied responsibilities was the artillery works, and it was here in the 1790s that he began to think about how he might be able to disprove the caloric theory using cannon boring. Rumford had noticed that the friction from boring out a cannon barrel generated a lot of heat. He decided to carry out experiments to measure how much. He adapted the machine to produce even more heat by installing a blunt borer that had one end submerged in a jacket of water. As the cannon turned against the borer, the temperature of the water increased and eventually boiled. The longer he bored, the more heat was produced.
For Rumford, what this showed was that heat must be a form of motion, and heat is not a substance, because you could generate indefinitely large amounts of heat simply by turning the cannon.
Despite Count Rumford's best efforts, Lavoisier's caloric theory remained dominant until the end of the 18th century. His prestige as a chemist meant that few dared challenge his ideas. But this did not protect him from the revolutionary turmoil in France, which was about to interrupt his research. At the height of the Reign of Terror, Lavoisier was arrested and eventually lost his head.
Once he was guillotined, his wife left France and eventually met Rumford when he moved to Western Europe in the early 1800s. Rumford then married her, so he'd married the widow of the man who'd founded the theory that he'd destroyed.
The marriage was short-lived. After a tormented year, Rumford left Madame Lavoisier and devoted the rest of his life to his first love, science. It would be nearly 50 years before Rumford's idea that temperature is simply a measure of the movement of particles was accepted. With heat, the particles, what we now know as atoms, speed up, and with cold, they slow down. Rumford's dedication to science led him to become a founder of the Royal Institution in London, and it was here that the next major breakthrough in the conquest of cold would occur. Michael Faraday, who later became famous for his work on electricity and magnetism, would take a critical early step in the long descent towards absolute zero, when he was asked to investigate the properties of chlorine using crystals of chlorine hydrate. This experiment was potentially explosive, which is perhaps why it was left to Faraday, and perhaps also why Dr. Andrew Shidlow is curious to repeat it today.
We are about to undertake an exceedingly dangerous experiment in which Michael Faraday in 1823 heated this substance here, the hydrate of chlorine, in a sealed tube. Is that sealed?
That's sealed, Andrew.
That's absolutely brilliant.
In the original experiment, Faraday took the sealed tube and heated the end containing the chlorine hydrate in hot water. He put the other end in an ice bath. Soon he noticed yellow chlorine gas being given off.
Because the gas is being produced, pressure's building up. Ray, this is where it starts to get dangerous. So if you now take a few steps back.
When Faraday did the experiment, a visitor, Dr. Paris, came by to see what he was up to. Paris pointed out some oily matter in the bottom of the tube. Faraday was curious and decided to break open the tube.
Right, so let's have a look inside here.
The explosion sent shards of glass flying. With the sudden release of pressure, the oily liquid vanished.
And there we are. Is that what happened? Yeah, that's exactly what happened. It popped open, glass flew. And can you detect the strong smell of chlorine?
I can now.
Absolutely. Well, he detected the strong smell of chlorine, and this was a major mystery for him.
Faraday soon realized the increased pressure inside the sealed tube had caused the gas to liquefy. And when the tube was broken, the oily liquid evaporated. Just as heat must be applied to evaporate water, he saw that energy from the surrounding air had transformed liquid chlorine into a gas. In a brilliant deduction, Faraday realized that by absorbing heat from the air, he had cooled or refrigerated the surroundings. Michael Faraday had produced cold. Later, he used the same technique with ammonia, which absorbs even more heat. He predicted that one day this cooling might be commercially useful.